And the talk of today is about the finite gap solution of the KdV equation with a geometric approach. Please.
Okay. Thank you very much, Davide. Okay. Before I start, I will thank you, the organizer, for inviting me to do this seminar. And also, I will just share to you that these are the reference about where I used to do my work, which are the growing knowledge of periodic and conditional periodic analogs of the Many-Solton solution of the KdV equation, which is the KdV that you see there, and the brought in another article, which is periodic problems for the KdV equation in the class of finite bands potential, and another article, they are pretty much all in the same year, which is Itz and Mathieu, Schrödinger operators with a finite gap spectrum and Solton solution for the KdV equation. Okay, now, before I start, of course, I would like to introduce some ideas of techniques that we will use in this talk. In particular, we will use the inverse scattering methods, which is pretty, well, not so recent, since it was invented in around the 70s. And it's a really powerful method to find solution and also constant of motions for the integrable PDEs, but not only for integrable PDEs. And then we explore as an example a particular case, which is the periodic problem for the solution of KdV, always via inverse scattering methods. Okay. So, what is the inverse scattering method and why the KdV equation is so important about it? Because actually it's like the first equation that we can find this application for this kind of methods. And indeed, in 1967, Miura, Kraskal, and all, in all a series of papers that you can find, related the KdV equation to some kind of Schrödinger equation or a so-called Sturm-Liouville equation, which is the following one here. And it's pretty much an eigenvalue problem. And so what they proved is that if we have another operator of this form here, then this equation is satisfied if and only if the potential of the Schrödinger operator satisfies this equation here, which is actually the KdV equations. Okay, as you can see, this equation is both dispersive and nonlinear. What is L dot? L dot is the derivative with respect to time. Sorry. So they depends on the parameter.
The operator that to function I substitute minus its Laplacian plus u dot times the function.
Yeah, sure. This is we can see as a the time derivative with respect to the operator. Okay.
So it's just.
I want to say that the derivative by the time from the derivation, and the derivation is nothing.
Yeah, but
so it's
I don't think it's nothing because when you do, okay, let's start with this discussion. Pretty much, if you d in the t of this operator here, you actually have dt of u x t. So I think the second derivation will be always okay. So, and but this is actually the first example of this relation here, and this relation actually 1 year later was well defined by Lux by the definition of what is called the Lux pair. So the Lux pair is a pair of matrices operator acting on an Hilbert space depending on a parameter t, such that they satisfy this equation here, which is called the Lax equation. And in the same paper, they also prove this theorem, which says that if you suppose that this operator depends also linearly, it's self-adjoint and depends also linearly on a function uxt, which depends on the space and time, and pretty much in the following way. So we have a part which does not depend on the function, and another part which actually depends on the function. And suppose that exists another antisymmetric operator which also depends on the same function, such that this is satisfied. Then the eigenvalues of this operator are integrals of motions of the following PDEs. And this is pretty much a new definition of integrability, different respect to the one that we all pretty much all know from Liouville.
Sorry, what is K?
K is the function that defines the PD.
Ah, okay.
Yeah. Okay. So in the same case, like in the KdV equation, we'll have that this is equal 6u qx plus u x. Okay. So yeah, it also can depend on the derivative of u. And actually, this is pretty much the start of this pretty recent method, which is the inverse scattering transform, which is follow the same. Now, we related the existence of two operators with the solution of an interval PD. So let's start for an initial datum u0. Okay, let's solve the scattering problem. So we have pretty much, let's solve the scattering problem LC equal lambda c at time t equals 0. So we have for t equals 0. This problem gives you for the boundary condition of the particular boundary condition of the initial value, gives you pretty much some data which is pretty typical to scattering data. That can be, of course, the eigenvalues, that you can be discrete or continuous, a spectrum, which of course eigenvalues which are in the spectrum, the refraction coefficient, and also a transmission coefficient. And with all this data, with a set of data that we call S lambda, now we can somehow evolve it in time, the data. How? It's pretty easy to say that if we derive with respect to time this equation, it's pretty easy to derive also the total equation, which means that the solution of the Lax pair of this scattering problem also evolves in time to the other operator that we define in the Lax pair. It's really exercise, and pretty much this kind of evolution is pretty easy, and it's actually this kind of nonlinear dispersion relation. So it's just this application here. And now there is so we have a scattering problem, an evolution which is trivial, but also we have another hard part which is the inverse problem. So now we have all this data which depends on the eigenvalues and depends also on the spectrum and also on time. And now we want to reconstruct the potential of our scattering problem.
Can you just say again what is S lambda?
S lambda are all the set of the scattering data. So it's something of this sort, like we have all our eigenvalues, discrete spectrum pretty much, lambda j's, we have the reflection coefficient, which depends on lambda, and pretty much describe the continuum spectrum of the operator, and we have also some kind of transmission coefficients. And also the normalization constants.
What other reflection?
Yeah, okay, the refraction and transmission coefficients. Well, this is because our initial condition sums asymptotics in x goes to plus and minus infinity, which can be like a constant of oscillatory of some other kind of backgrounds. And so what we actually study is the solution when x goes like to minus infinity, and also the solution when x goes to plus infinity. So in the middle we have just to reconstruct and let that these two solutions coincides. And this kind of in this way you actually find some kind of transformation from this type of solution and this other type of solution that gives you the reflection and transmission coefficients.
I think they usually define like you take the absolute value squared, say plus and say minus, you take the difference divided by the sum.
Yeah, it's usually
There's a lambda in our equations.
Ah, yes. Thanks. It's okay.
One more question. What
Yes.
do you mean as the multiplication of exponent?
It's not well defined. Pretty much, it's just to say that when they depends on time, it's pretty much trivial. Well, these are constant. This is something of this form, and also this one. Yeah. This is what I mean when I say multiplication on the with the e to the minus I. And this is pretty much a general. This is really a general consideration of the evolution equation. Okay. Any other questions?
Then how do you reconstruct u of xt then?
Well, there are a lot of techniques to reconstruct it. Usually there is integral equation, which is the Marchenko-Levitan equation, which is pretty standard. But also you can reconstruct it with other methods like Riemann-Hilbert problem.
So given the data, you have some recipe to.
Yeah, sure. And in particular, in this talk, we will see another way, which is pretty much constructing for these cases. Okay. Then, of course, after the paper of Lux, people material physics is working on interval system and start also to apply this kind of technique also to other equations. The first one, the second one actually is the nonlinear Schrödinger equation, which so thanks to the work of Zakharov and Shabat, we actually find a Lux pair for the nonlinear Schrödinger equation. But also 2 years later, Ablowitz, Kalk, Newell, and Sigur generalize this kind of procedure. So in a way that you can actually find Lux pair for pretty much all integral PDEs. So like modify KdV, sine Gordon, and so on. Is a pretty standard procedure. And also, yes?
Just a question about
names.
Like you said that like, they were able to find like a Lux representation of any integral PDEs. But you said that like PDEs in relief you can find out Lux.
Of course. Yes, we know that it's interval, but we don't know that they Lux pair.
But we
Yeah.
knew before
But
finding that it's not integral.
Well, it's not because actually, well, you can prove it that PD is integral by finding the constant of motions. But actually, this procedure.
With this procedure, if you have an expert, you have the constant of motions. So
of course, also this way.
And also, you have this recipe to solve the inverse problem.
Yeah, because this is really important. This definition is pretty important because it gives you actually also a algorithmic way to find a solution to the PDs. And also pretty much because okay, we know that these PDs are integrable, but finding a Lax pair is pretty much it's not so easy. And so what the Albrits now Newell and Sigor found is pretty much a way to find a Lax pair. Actually, they're all the procedure is explained in a book which is here in the library, which is Albrits Sigor, and it's inverse scattering transform and soliton theory. There are like the first chapter is pretty much dedicated to all these things and also the proofs, and also you find also how to do the inverse problem through Riemann inverse problem. Okay, and also another important thing is that thanks to Abrowitz and Ladding, they also generalize this procedure to discrete interval system. So in the same way, you can find a Lax pair for a discrete interval system. Okay, now one question is, it's pretty much valid for every initial condition. It depends, but because this procedure, of course, depends on what are if there exists a solution to the scattering problem. So it may depend on the potential itself and also on the domain when the potential is defined. But also it depends on the existence of inverse problem. An example that I can say is that if our initial condition is defined on X inside the reals, for KdV, we have a condition on the we have actually a condition on the initial condition which is pretty general, which is the following: no, minus infinity plus infinity of 1 plus x u0 of x must be finite. This is called the Faddeev condition.
And this gives you a Hilbert space where you want to solve your eigenvalue.
Yes. Okay. Now, let's talk about the periodic problem for KdV. So now, what I want to show you is to solve the KdV equation for initial conditions which are periodics. So we have some kind of period in the space. And now we want to apply the inverse scattering methods. Okay.
So this is very different from the condition because
yeah, but actually you can show. Well, the periodic is I don't think it's so different from the condition. I have like to try to do it some periodic. Okay. Well, let's okay. Let's start with the scattering problem. So now we have our Schrödinger equation, and with a periodic potential. This actually is a actually a well-known equation called the Hills equation. So pretty much we can find some kind of solution to this equation. There is also a book about the Hills equation. So now we consider this a basis of solution called C and S, where x0 is just a condition that gives us a normalization to this equation, which has the following, where this sign here means derivative with respect to x, and this will be our basis for the solution side. So it's important because the wrong sum of this basis is finite. It is equal to 1 for every x. Okay. Now we have a definition. Let's first see which are our first scattering data, which is the spectrum of the operator. We call the block spectrum or stability zone the set of all the lambda which are real, such that exists a solution for our scattering problem. So let's start by see how this spectrum is the form of this spectrum. And actually, we will see that this is given by finite intervals, and I will show you how it's easy to prove it. To prove it, we have to define a monodromy operator, or just a transition operator, just which gives us a transition respect to the period of our solution. And actually, we can write it in a basis in our basis of solutions, and this gives us a matrix which has this one here. And we denote with mu, the eigenvalues of this matrix, which is given by this really simple formula, where this delta is the half of the trace of our matrix.
Can you say again who's S and C?
S and C are generic solution, are a basis of solution for the Hills equation. It's pretty standard to call it C and S because it reminds you sine and cosine, but actually they're not sine and cosine. It's pretty much different, but in a particular limit and particular potential, they coincide with the sine and cosine.
For u equals 0. For u equals 0.
For
u equal a constant 0.
Yeah. Yeah, sure. So just a deformation of this solution. Okay. Now let's fix our eigenvalue, and it's really easy to see that if the solution of our scattering problem must be also an eigenvector of the monodromy operator. So we have these two conditions. And in particular, in physics, this kind of solution are called the block functions, and it's pretty common to see it in when you study in solid-state physics, where you study like electron that pass through a reticle of atoms. And now we have this lemma that says that it gives you actually bound of say which form must have the eigenvalues of the monodromy operator, and pretty much says that if lambda is in the block spectrum, then the monodromy operator must have modules of equal to 1. This is really easy to prove because we just need to apply the monodromy operator n times to our solution. This gives you something of this form, and it's pretty easy to see that if I go to x goes to plus infinity, this is unstable because the solution goes to plus infinity. For mu, which is greater than 1, while for mu, which is smaller than 1, we have the same thing, but with the minus sign. So we have that the module of the eigenvalue of the monodromy operator must be of modulus 1. Okay, because the modulus of the solution must conserve. It's okay. So now we know that the modulus must be equal to 1. So, and we know that there is a formula for this eigenvalue. So let's check for which values of the delta, the modulus of the eigenvalue mu is equal to 1. In particular, if the delta is greater than 1, then actually we have that the mu are reals. But so this means that we have a mu which is greater than 1 and a mu which is smaller than 1. So this means that the solution is unstable. So whatever lambda gives you half of the trace which is greater than 1, then that lambda must be outside the block spectrum. Meanwhile, if we have a delta which is greater, which is smaller or equal than 1, then we have that the mu are complex conjugates, and so that the modulus is equal to 1. So the lambda is in the box spectrum. So now we have a condition such that our eigenvalues are in the block spectrum. This is pretty much how it must work. We have the lines -1 and 1. This is delta. So in this side, our solution is unstable. Then from here to here, it's stable. Then here is unstable. Then from here to here is stable again, and so on. So this side here and these two eigenvalues gives you an interval which is our block spectrum. And so this one, and so this one, and so this one, and so on. Meanwhile, we have the gaps, which is the following one. This is pretty much how it works. I use it like these are given by C and S, which are known as Mathieu function, and it's just how it must work. Just plot it just to show you how must work. Okay. So now we know a form which that the block spectrum must be a set of intervals, which can be finite or infinite.
So I mean the numerics, the real numerics for which iterator.
This is it's not so much numerics. I just take the Mathieu C and S function. I just calculated the delta for that C, and I plot it in a symbolic way with Mathematica.
So this U, what is U? What is
no, the U I think is the Mathieu function is the cosine. Yeah, it was a plot just to show how the logic must be. Okay. So now let's talk a little bit about the property of the zeros of this the solution of this equation. Okay. Of course, the root must be almost double. And if the root is simple, this means that our monoidal matrix cannot be reduced in a diagonal way, which means that the off-diagonal term are not zeros. And which means that we have only one eigenvalue. While if it's at least double, this means that we have a degenerate level of the spectrum of the periodic and anti-periodic problem. And so we can reduce it in a diagonal way, and we have two eigenvalues. So which means that the off-diagonal term is equal to 0. Pretty much, if the root is double, we can see that if here is 1 and here is -1, we have some kind of things of this form, where all the block spectrum is given by all this interval, and we have a -0 here, which pretty much coincide with the Soliton solution. Yeah. So we have a shrink of the gaps, of the gap. And pretty much these things. Okay. So this is what. So this means that the boundaries of our spectral gap must be just simple roots. Okay. Now let's talk about our solution and how we can route it in with our basis of standard solutions of the Hills equation. And we choose a normalization of this form so that at x equal x0 is just equal to 1. So there is this lemma which says that our psi is written in C and S in the following way, and we actually have a form of this B, which it does not depend on the x, but just on the x0, and are just given by the terms in the monodromy matrix. And also here is pretty much easy to prove it because an idea is just that you apply the monodromy operator to this ansatz. So we have just this T mu T C equal to mu C, and since we know how this operator acts on C and S, but just think that we have a matrix T and a vector C and S of this form here, and then if we compare it, we find actually that the B must have this form to be also a eigenvalue of the solution. An eigenvalue of the monodromy operator. And now we define also another function which is now independent to this x0, which is this key plus and minus, which is just the minus side, the logarithmic derivative of our function psi. And it has this property. It's independent on the choice of x0. It is a periodic in time. It satisfies the Riccati equation. Also, we have a link between the imaginary part of this psi and the real part of this psi, and admits an asymptotic expansion of this form here. Okay. All these properties are really easy to prove it. In particular, the Riccati equation is we just put this ansatz here to the Schrödinger operator. And this asymptotic expansion is given by a technique which is called the WKB technique. Serious, yeah.
Just a question. Then, like the lambda that is going to infinity is like with the condition that lambda should lie in the Bloch spectrum. Right?
Yeah. Because then we saw that we choose a Bloch spectrum just that we have this kind of this band here.
Oh, sorry.
Yeah. No problem. Okay. And now we have this lemma, which gives us actually a form to this C, which is the same of the same of B. And to prove it, this lemma, this is really easy because we just need to calculate I C x0 lambda, which is equal to psi prime x0 lambda over psi x0 lambda. But this is equal to 1, and this is equal to B. And so, because we have the normalization on the C on the S. And so, this is proved. Now, let's see. Now we have our solution. We have our Bloch spectrum. Let's try to understand how we can also reconstruct our potential. Now, so we have, let's consider that we have a U with just only a finite number of spectral bands, which means that, as I said before, we have also bands which goes to plus infinity. So they are odds. we have all the number of these simple roots. Then we consider a Riemann hyperelliptic surface. Now, what is a Riemann surface? It's just a 2D compact manifold in C. And pretty much they are described by this algebraic function, where instead of 2 we have some kind of n. And what does it mean this? Well, this means that well, this kind of Riemann surface is just given by a gluing of 2n minus well, let me think a little bit. A gluing of 2 complex plane, because how many complex plane are given by the exponent here. So we have some kind of this complex plane with these bands here, and we are gluing 2. So we have this kind of C that equal 1, this kind of C that equals 2. So these are pretty much different, and we are gluing band by band this complex plane. Topologically, what it gives us? Well, some kind of n torus. Okay, this is pretty rough. What does it mean? This what a visual gives you a visual of what is this hyperelliptic surface here.
Yeah.
Yes.
Your first picture doesn't look to be compact.
Hmm? Ah, yeah. Of course, we need to consider also the quantitative. we must have some kind of a bubble with this must be the picture. So we have Riemann spheres with cuts, and we glue in every cuts. Thanks, Pierre. Okay, and pretty much what we will see is that this surface has the topological properties, which is given by the homology group. But also we can define a differential on these Riemann surfaces. So we have differential properties, and also we can define function in this which lies in this surface. And pretty much in this talk we will use everything of these things to solve our inverse problem. So we have this hyperelliptic surface where the branch points are given by our plot spectrum. Now, if we consider this kind of now, since pretty much the roots of R and 1 minus delta size, yeah, pretty much we just consider this is given just the simple roots of the 1 minus delta square. So which means that this function is gives us the double degenerate roots of our of 1 minus delta square. And we know that these double degenerate roots are actually zeros of T1, 2 and also of T1. So we can write T1, 2 in this form here with this function here. That actually it's really easy to prove that is a n-order polynomial, and we will see it right now, because now we have this theorem that gives you another form to write our Xi in with this new formula that we find in this with our Riemann surfaces. And now, well, this is pretty easy to show because we just have to substitute the T12 in the previous formula that we find, and actually, since this key must have an asymptotic expansion that we saw before, this gives us also the proof that the P is an polynomial in lambda. It's an order polynomial respect to lambda. And now, so what we have to just do is to find out which are the roots of this gamma j, which are really located outside the block spectrum. This is our last thing that we have to show. Now, since this gamma j0 are roots of this T12, so which means that actually these are eigenvalues of the Dirichlet problem with of our scattering problem. So it's eigenvalues of our scattering problem with Dirichlet boundary condition, which are this one here for this segment here. And now, by some properties, we find out that actually this lambda are not inside the block spectrum, but since these lambda are our zeros of this, but also must stay inside the block spectrum. These or are in the boundaries or are outside the block spectrum. And so we prove also the theorem of before. And it's important, this theorem, because right now, from now on, we will use this form. This one. It's important because for now on, we will use this formula a lot. Okay. Any question? Good. So, as consequence of this theorem, now our function key is a single valued algebraic function on our Riemann surface. And so, which means that our eigenfunction is just a continuous monomorphic function on our Riemann surface, except the infinity, with n simple poles where lambda is coincided in the gammas, and n simple roots when lambda is in gamma x0, and n simple roots where lambda is in gamma jx. And also he has this expansion here. In particular, it's important that there are simple poles because that means that these simple poles are just located in one of the sheets of the Riemann surface. So, which means that in the draw that I saw you before, so something of this way, the poles live just one here, one here, one here, one here, and not here. So we consider, without loss of generality, that all the poles are in one sheet, because eventually it can be also alternative. So we fix just the sign of this sheet. Okay, now we have all our data, which are the boundaries of our spectrum, our block spectrum, Qn plus 1. The eigenvalues of the monodromy, the eigenvalues of the monodromy operator, but also the poles and the zeros also of the diagonal terms. So now I will show you how, starting from this data, we reconstruct ux. And to do it, we need to first see how our gammas varies respect to the derivative respect to x. This is an equation which is called the de Broglie equation. And the proof is really simple, because since we have that the poles lives in one sheet, in the other sheet, we must have the denominator is equal to 0. So, which means that we have this differential equation here. But since this is also equal to this one, we can write it as in the equation here. Because since we have also, we know how the form of this polynomial, and these are pretty much the its derivative, so we can rewrite it in the same way. Of course, we don't have anymore the sum, because when we choose just one eigenvalue, the other one cancels except the one without it. So, and now we have also we can have also a formula for our potential, which is just given by -2 the sum of all these all the roots of the Baker function, which is our c, and plus the sum of all the points of the the endpoints of the block spectrum. And also, this is really pretty easy to prove, because if we use the lemma 4, which is the lemma with where we define the key and these properties, from the asymptotic expansion is we put the asymptotic expansion in the Riccati equation, and it's really easy to see that the first term of the expansion is just equal to minus our potential. Then, using the theorem that we saw before, we see that for lambda goes to infinity, only the real parts survive. And if we expand it for a lambda that goes to infinity, we have this expansion here. And this is our Q1. So we prove also this part here. And this formula is really important. But now, the main question is, which form has this sum here? And to find an answer to this question, we need to introduce an algebraic problem. But first of all, let me, we have to introduce an algebraic problem, which is the Jacobi inversion problem. Okay, so let's define a canonical basis of cycles in our Riemann surface, which means that we have a pair of alpha j beta k such that the intersection number between j and beta k is 1 only if j is equal to k. So we have this form here. Meanwhile, the intersection number between each other of these cycles is equal to 0. Okay. This image gives us an example of this canonical basis. And also we consider this is a typo. We consider a basis of holomorphic differential, which is given by this omega here, such that are another type of normalized respect to the integrals on the alpha j's. So which means that if I take the integrals of the alpha j's for an omega m, this is equal to q pi I, the Kronecker delta when only when j is equal to m. And also we can define a matrix B given by the value of this integral here. So the value of the integral of omega respect to the beta cycles. Okay. This matrix is really important, and it usually is called the periodic matrix, and we see then why. Now we can define a change of coordinates from a set of points in the Riemann surface to a vector space in Cn. So we have something of this form here. This tau gives us points from in the Riemann surface to some subset of Cn. This subset of Cn is called the Jacobi variety, which is indicated in this form here. And component by component, this is the formula of this map, which is called Abel map. So now we introduce the Jacobi inversion problem, which means write the point in the Riemann surface such that in terms of the components in the Jacobi variety. Okay. This is pretty much it, and it's really enough stuff to find out, because it's some kind of nonlinear algebraic equation. But you can actually find inverse mapping to that. And pretty much to define inverse mapping to them, we need first to derive this Abel map to respect to our parameter x. So pretty much this is pretty standard. So this is just the derivative, since it's an integral and the times in the integral is defined to x. We have this standard from these things here that actually we know from the de Morgan equation the form of this one, and this gives us this rational equation here. But this, we can actually write this as a sum of residue of lambda respect to gamma j, and the sum of all the residues is equal minus the residue at infinity. So we need just to check which are the residues at infinity of this algebraic function, which is just given by this component here. And we call this component phi m, because actually this component coincides with the residue at infinity of our gamma m. Because actually when in our differentials, when the lambda goes to infinity, we can rewrite it in the following way as phi m c dx, where c is equal to 1 over the square root of lambda. It's pretty easy to find out. It's just a change of variables and just taking out the terms. So which means that when c is equal to 0, we have lambda that goes to infinity. Okay. So, but we actually need to know every single point gamma. No. For us, it's enough to find out which are the sum of this gamma. So we define a function which is this f here, such that the section of f respect to the Abel map at x0 gives us this pretty much this function gives us the sum of all these points. And actually, we can write this function as a sum of residues of a function in the Riemann surface with poles are pretty much in the Riemann surface, the poles that we have already defined. And this function, and pretty much we can rewrite this kind of sum in the following way. Now, what is this theta? This theta is called the Riemann theta function, and it's defined in the following way. I cancel everything. Which is, I wrote it so I cannot get confused. This is a function on z, where z is in Cn, and also it depends on the periodic, what we call the periodic matrix, and it's given by the sum of m in Zn, the exponential of 1/2 m transpose Bm plus m dot z. Okay, it's some kind of a generalized Fourier transform, but with 4 factors. This is actually called multi-periodic Riemann-Hilbert. No, Riemann-Hilbert, multi-periodic Riemann theta function. And actually, it has also some conditions, like that it's periodic respect to translation equal to and also if we translate it respect to the m, we have that it's almost periodic, so that like respect to some kind of m beta n is I don't pretty much remember, but it's just a function which depends on n and beta zb. So it's almost periodic. So we have this really bad formula, but actually in our cases here, it became pretty easy, because this one just gives us a constant, and this is what we are interested in. In our cases, this actually coincides with one residue at infinity, and so we calculate this residue, which gives us, well, our psi e, and is what we have defined before, and we find this formula here that actually we can rewrite in this way, where this u are actually equal to our 2i. This uj is equal to I n minus 1j. See, yeah. Okay. And so we have this kind of vector u. But this is for x0. But what about gamma jx, which is what we are really interested? Well, there is a theorem by Kaiser, which say just that the Abel map for the gamma 1 to gamma n, which depends on x, is just given by this Abel mapping plus ux. So it's just a linear evolution. And so we can rewrite it, our potential, in this way. Now, we found the scattering problem, we defined the inverse scattering problem. We just need to understand the time evolution. Okay, it's pretty much easy to just a straight calculation to see that since we have this identity here, it's easy to see that our psi dot must satisfy this equation here, which we can rewrite in this form here. And it's such that we have also this C here. And we will see why this C is important. Of course, we found also how to define our beta function, this beta, which is a function only on x0 and lambda. But if we differentiate this equation with respect to x, and then we put this psi, we divide everything with respect to psi. We actually can write it everything in respect to c, such that we don't have any more the dependence on x0. So we have this equation here, and it's important because if we use the theorem that we saw before about how the form of our key, we can really see that the polynomial p, if we derive with respect to time the polynomial p, must satisfy this equation, differential equation. Now, if we restrict that in the point outside the gap, we found actually another equation, which is always called the de Broglie equation, and it's really similar to the de Broglie equation, as you can see. So all the things that you have seen before, we can reapply it, and actually we can see that in the end, our finite gap solution has this form here, where we have where our Abel mapping of a linear evolution in the space and a linear evolution in time. Okay. Now I've just finished my talk. I'm just saying that this pretty much is standard things. If you want to know what I'm actually doing in my life, I will also talk at the Junior Geometry and Mathematical Physics seminar, pretty much in the middle of April. And the topics will be a little bit different because we'll talk about the inverse scattering for NLS. Instead of this algebraic geometry problem, we saw some complex analysis like Riemann-Hilbert problem. Also, we introduce solitons and the concept of soliton gas. Thank you very much. Too fast? Okay.
Thank you for your nice talk. Are there any questions? Maybe from home.
Can we summarize, I don't know, in a fast way that was, I don't know, that was done. So we have like this given surface, we have some points with asymptotics that we need to satisfy, like, that comes from the equation. And we have these nice vector functions. And after this, if we satisfy our asymptotics somehow from our equation, we can construct the solution from these guys.
Yeah.
Asymptotics, and at that point we are already happy because we like we made the solution.
Yeah.
So that is like ablothostatic. But
It's
is it like the ablothostatic lattice? I mean, like the idea of construction.
yeah. It's the same. Actually, I already say that ablothostatic lattice is a generalization of the inverse scattering transform. Actually, this is pretty much also generalization of the concept of multi-soliton solution, because when the multi-soliton solution is just a limit of this solution when we have that all the branch sinks to a point. Yeah. And so we don't have anymore the condition of periodicity, but we have this multi-Soliton solution, and we don't have also the reflection coefficient. Okay.
If there is no other question, let's thanks.
No, wait, there is some.
There is.
Sorry.
Maybe just a curiosity. Like, what happens if the gaps close?
In which sense?
Like we saw that basically, what in the generic case we have the dot spectrum.
So if you have infinite gaps, we have an infinite genus solution.
That's not complex, I guess.
I think that no, I think that you still have compactness.
Okay, but like
it's difficult to compute, but you still have compactness.
But is the Jacobi version solution still relevant in that case?
I don't know, but I don't know, but this kind of argument, and the fact that infinite genus solution is used when you have to describe also the Soliton gas, because recently they use this kind of solutions. There are a lot of methods to study Soliton gas, and pretty recent works of Gennady L, Tobvis, Alexander Tobvis, and others use the fact that of existence of they take an infinite genus solution of KdV or MLS, and then they shrink the bands, and they see and they try to see how more than the solution, how the velocity of the solitons change in time, and so pretty much they try to check how the velocity of the soliton change in the gas, and so what they do is to derive some synergetic equation for the Soliton gas, starting from shrinking banks to infinite gap solution.
So they do use this kind of techniques?
Yes. Yeah. Because also they define this nonlinear algebraic equation, but not in respect to the holomorphic differential, but other meromorphic differentials, and they pretty much use this technique, the same technique. They just expand it a little bit because they taking the limit of closing bands. Yeah, there are a lot of articles about it, and it's really interesting to see. I personally use another method to study the Soliton gas.
So I think that we can really thank you. And see you next week with a talk by Lorenzo.
Dear.